Yeah, so good morning and welcome to this lecture on route planning. So what I'm going to describe to you is, so you learned about Dijkstra's algorithm, and I'd like to discuss like how to implement Dijkstra's algorithm in your project and what else is there to do. Like when you think Dijkstra's algorithm might be too slow, is there a way to speed things up? And there is. Let's start with something else, and that is, you should have received an email from Learnit that Rasmus wrote, and it's the Studieprozess-Samtale. And that starts like right after this class. It's at 12:30, it's in auditorium 2. And what it is about is that there are all these Studie-Vejleder at ITU, and they kind of want to know like how does studying at ITU work for you. How it's going to work out is that like each Studie-Vejleder will get like a sample of people from your group. That will be like 6, 7, 8, 9, and you will discuss with this Studie-Vejleder. Okay, it feels a bit weird saying this word all the time. They will ask you questions, they will discuss like your progress, they will discuss problems that you have, you will have the chance to discuss among each other, like how studying the software engineering program at ITU works for you. And it might be a good opportunity for you to discuss with your fellow students. It's also a very good opportunity for them to actually see like how does this work. I mean, usually, like, we see you and we discuss things with you, but people from the administration, they usually don't see or they don't really regularly talk to you. So this is their chance to actually see how does it work, and they will come back to us and say, okay, like, I know you have talked to these students quite a lot, but like, if teachers aren't around, they tell the following things about how things might be improved. And that helps a lot for us in improving or trying to improve like all these classes that we prepare for you. There's this third bullet point here. I don't know, like, so before you start, you should find out what are the 3 most surprising things when you started at ITU. I mean, I don't know. It would be interesting to see what you say here. Yeah, but long story short, it's completely voluntary. You go there if you want to go there, but it helps a lot in the process here at ITU. So please consider joining this. And it starts at 12:30 in auditorium 2. Let's do route planning, and we are not talking about, or I don't want to talk about this guy's route planning. I rather want to talk about like route planning in this little device over here. That's what we are going to do. And let's first discuss the problem. You should have seen Dijkstra's algorithm last week. Yes, and yesterday as well. I mean, yeah, you've seen quite a lot of different things. I think like some of the TAs, you were very smart and clever. You said to the TAs, like in this algorithm and data structure course, this Dijkstra algorithm presentation maybe was a bit, like it was at the very end, it was a bit short. So some of you like consider that it might be too short, and you don't know if you're going to understand all of these things. That's what I told Tore as well. And he might caught up this and did it yesterday again. So you have seen the algorithm, you have seen the problem, but you have also seen many other algorithms that go in kind of the same spirit. So you computed, like, what did you do? You had DFS and BFS to explore the graph in different, with different properties. You consider this single source shortest path problem. Dijkstra's algorithm is an algorithm that solves this problem. And there was this somehow closely related problem of computing minimum spanning trees. And there you had like an algorithm called Prim's algorithm. And it was like very short. If you implement both of them, it's like a one-line change. And you come from Dijkstra to Prim's algorithm and the other way around. Although the problems are pretty difficult in nature. We are going to talk about the single source shortest path problem. The input is a graph, and it's directed and it's weighted. Yeah, that means that you have this C function here that gives every edge a weight. And you have learned about these weights, or at least I hope that you did, that in Dijkstra's algorithm these weights are not allowed to be negative. Yeah, they are only allowed to be non-negative. 0 is okay, positive is okay. I don't know, did you ever see what the problem is with negative weights? Yeah, okay, perfect. Okay, what is the task? Okay, one student kind of saw this, but we'll talk about a modification of Dijkstra's algorithm, and maybe when we discuss why this works, I can only also tell you what is this problem with these negative weights. Like they can, like as soon as you see a negative edge or an edge with a negative weight in Dijkstra's algorithm, you can't be sure whether this is correct or not. Dijkstra's algorithm is going to tell you something, but you just don't know whether it's correct or not. And in the proof, you will see why this is the case. Okay, but what is the problem? So you see this graph, and I give you a source node S. And what I want from you is that you compute either the shortest paths from S to every other node, or even simpler, just the length of all of these shortest paths. Okay, and Dijkstra's algorithm solves both of these problems. And just for future reference, like the length of the shortest path between S and V in our graph is denoted by this DSV. And there's this example, I hope you should be able to at least see it. Somehow there is this graph, and we are going to run the example of Dijkstra's algorithm on this graph again. But just like this is a question that you can just solve by looking at this graph. Yeah, Dijkstra's algorithm is an implementation, is an algorithm to show you this is how you find shortest paths. But for example, here I ask what is the distance, the length of the shortest path between our source node S, 0 over here, to node 5. Node 5 is down here. And you can just, you can look at the picture and see what's going on here. So there are many paths from 0 to 5. Let's look at some of them. So there is this path over here. Yeah, which is 0, 1, 7, 5. The length of this path is 5 plus 4 plus 6 makes 15. One candidate for shortest path. There's another path here, 7, and then from 0 to 7, and then to 5. The length here is 14. There are other paths. 9 plus 5 is 14, plus 6, that's 20. And there's 9 plus 4, that's 13. There are 4 paths, this path of length 13. That's the shortest path. Okay? And this is just enumerating all of these paths and saying the one over there, that's the minimum path. Dijkstra's algorithm is going to do this much smarter than I just did. Okay, you can ask the same question, what is the shortest path between 0 and 6? 6 is all the way down here. And now there are many paths to enumerate. The shortest path, we are going to see it in the example, but it's going to be from 0 to 4, that's a 9, to 5, plus 4 it makes 13, to 2 makes 15, makes 13, 14, 25. And there are other paths like 0, 4, and then to 6, and that is 29. Okay, that's the problem. Yeah, given one vertex in the graph, compute the length of all the shortest paths. Dijkstra's algorithm solves this, and we are going to do some live coding. But let's just discuss what is the idea here, and then we have to implement this idea as efficiently as possible. We are not going to do it very efficiently here in class. You can do this in your own project. What's the data structure? Let's assume that our vertices, as in the example, are just numbered through. And for me here it's 1 to n. N is the number of vertices in the graph. And you need 2 arrays in this view that you also saw in this algorithms book here. The first array is called dis2. The other array is called edge2. And the idea is that your dis2 array, the dis2 of a node V is the length of a shortest path from source to V. So at the end, dist of 5 should be 13, dist of 6 should be 25. In between, the algorithm is not sure what the actual value should be. We'll see like how it updates this value all the time when it sees something new. And then there is edge2. That is if we are interested in the actual shortest path, like how does it go through this graph. Then edge2 of V is the vertex of the last edge on the shortest path from source to V. We also see this in the example. So it's like when you go on the shortest path, what was the node before V? What is this last edge? How does it look like? And we'll see from this, we can actually infer like how does the shortest paths, how do they look like? Okay, and there is a basic operation called relaxation of an edge. So you see an edge from V to W, and you always ask yourself the question, does this edge improve my current knowledge of shortest paths in the graph? So more specifically, you ask, is the distance to W that I know larger than the distance to V plus the cost of the edge? Okay, so we already know how to go to V in dist2 with length dist2V. So we have this path to V, and then we add this edge. That's a path to W, and we compare it to what is the current best known value we know to W. Does it improve this? Is this a better path? And if it is, we update our dist2 value to W to be exactly of this length, and we say, well, the last node on the currently shortest path to W, that is our node B. Okay, and then and we'll see when we implement it how this works out. Dijkstra's algorithm on a very, very high level, and I'm actually a bit unsure, like, if this really helps you, this very high level, or if you need to go somewhere deeper to actually understand what's going on. But now the idea of Dijkstra's algorithm is, like in BFS or DFS, considering like adding nodes one by one to the currently explored graph. And the order in which you add nodes is increasing distance from our source. Yeah, and when we add a vertex to our tree, or when we add a new vertex, then all we do is we take our node, we look at all the outgoing edges, and we use this relaxation operation on those. And that's all we do in rounds. Okay, let's look at an example. And I guess you have seen this example before, but it's going to be, I think it's going to be useful. Okay, so this is the example, the very same example as before. This is our input graph. We see our edge weights here. It's a good question how this graph is actually represented. Yeah, and here, for example, we have a list of edges, and each edge comes with its weight like this. In your project, you choose it yourself, and I will show you a different way to store a graph. But I would say, like, choose whatever works best for your project. Like, choose whatever you feel most confident is the right graph presentation. We'll talk about this a bit later. Okay, how does it work? So this is our input graph. We want to find all the shortest paths from our source node S here. Okay, and we have two arrays, dist2 and edge2, and we only see the values that are currently of interest to the algorithm. There's initialization. Initialization is you go to your source node 0, and you say the distance from the source to the source, that is 0. Okay, this is a value where you can be sure of. But this is also something that is highly dependent on your input. Yeah, because it could look, and that's a problem for Dijkstra's algorithm. It could look like this. 0, 1. So this is our start node S. Let's say this is -3, this is 1, this is 1. Then what's the length of a shortest path from S to S? It's kind of, we don't know. Yeah, it's not well defined. Yeah, it's like I go one round here, and the length is -1, so it's not 0. I go another round, it's -2, and usually you would say that it's not defined here. Yeah, it's -infinity. So there is this negative circle. There's a circle of negative length. Okay, but this is where the input is. This is forbidden as an input for Dijkstra's algorithm. Okay, and there are other algorithms which they just run, and they will tell you at the end, by the way, there is a negative circle here. And this node is on the circle. And you might have seen such an algorithm as well. It goes under the name Bellman-Ford. No. No? Okay. So there's this. Okay. And that one is even easier. This is like a 3-line implementation. It's just calling relax all the time. And after a certain number of times, you call one more relax, and if it still improves the situation, then you know there's a negative circle in there. It's quite nice, but it's very, very slow, and you can't find routes using this algorithm on the map of Denmark. I tried. Okay, this is forbidden. So we know the distance, the shortest path from 0 to 0, that is 0. That is the initialization. And then we do rounds. We ask from all the nodes we have seen so far that have a dist value, what is the one with the smallest distance? And it's this node 0 here. That's distance 0. So we take this node from somewhere, and we call this relax operation. And for this relax operation, there are two things that are important. It's the number over here. That is the distance from the source to this node, and the edge weight. And you can always compare it to the currently known distance to the other node that is on the other side of the edge. Okay, so what does this mean? So we start setting all the other distances to infinity, but this is something that you basically do virtually. And what we do is we know there is no path basically to node 1. And we know there is a path, but there is a path of length 0 plus 5. There's one of length 5. Does it improve the distance to node 1? Yes, it does improve the distance to node 1. And we would say, okay, the distance of this 2 of 1 is now 5, the sum of these two values. Same here, the distance to 7, we have a candidate with 8. That's better than infinity. So we say the distance to 7 is 8, and the distance to 4, that is 9. 0 plus 9. And that's what we update. That's one step. That's the result of the relaxation. And we store in this edge2 value. Here in this implementation, it's the edge that was used to come from vertex 0 to vertex 1 with the in distance 5. Okay. Now, node 1 is done. And it's, I think, I don't know, like at my previous university, well, we always taught Dijkstra, and the main problem that students had was this, you do something in rounds. Yeah, and at every round, you look at where you currently are, you look at all the vertices that now could be the next choice, and you take the minimum. So what you do here is, you forget about this graph, you only look at this array, and you ask, what is the vertex with the currently smallest dist2 value that I haven't seen so far? I have seen 0, it's grayed out. So candidates are 5, 8, and 9. Well, the smallest one is 5. And that's where we make our next round. So we take node 1, and we do the very same thing. Yeah, and from now on, it's round by round, take a vertex, relax all the edges, done. That's Dijkstra's algorithm. Okay. Let's do it very slowly. There's node 1. We look at all the edges that are outgoing edges, and we compare. 5 plus 15, that is 20. Against infinity, 20 is smaller, so there is a better path to 3, and that one has length 20. 5 plus 12, that is 17, better than infinity. So we have a better path to node 2, and we update the dist2 value. 5 plus 4 is 9. We compare it against 8, and this is worse. So for the first time, there has already been a better path. So this edge here doesn't help us. We know that there is a path of length 8. This tells us there's also a path of length 9, but we are not interested in this path. Okay? So there are some new values, 20 and 17, but some of the values didn't improve. And that is this little check mark down here. Okay? And so on. Next round starts. We look at all of our nodes. We have 4 candidates to choose from. And this is really, I mean, it's something global. Sometimes, like in an exam situation, you say, what do I have to do? Like next round in Dijkstra is, this edge here was the lowest edge, I have to follow that one. So you do it greedily among smallest edges, like Cream's algorithm does it. It's really important to say, we stop, we look at all of the candidate nodes, and we choose the one with minimum weight. And that one is node 7 with a dis2 value of 8. So we take node 7, we look at all the outgoing edges, we do our computation, 8 plus 7 is 15, it improves this value here, so we have to set this 2 of 2 to the value of 15. 7 plus 6 is 13, there has not been another way to 5, so this also improves the situation. So those values are updated. This was this round. Next round starts. Among all these 4 candidates, what's the smallest value? It's vertex 4 with a value of 9. So we select it, we look at all the outgoing edges, and we always do this calculation. 9 plus 5, that's 14. That's worse than 8, so we don't update this value to 7. 9 plus 4 is 13. That was 14. 9 plus 4 is 13. That is better than 14, so we update this value. 9 plus 20 is 29. It's better than this value down here, infinity. So we update these 2 values, but this value 8 here remains. Next round starts, 4 candidates. Round vertex 5 is the next one. Here, same calculation as always. 13 plus 1 is 14, is better than 15. We have to update that one. 13 plus 13 is 26, better than 29. We have to update that one. Okay. 3 more nodes. The smallest one is now node 2. And we relax all the edges. 14 plus 3, that is 17, improves. 14 plus 11 is 25, improves that value. Both values are updated. Then there is, these 2 nodes remain 17 and 25. Okay, and now we relax this edge. 20 plus 9 is 29. Nothing happens. This value is correct. And then there is node 6. No outgoing edges. You're done. That's the output. These 2 values. Now if you ask what is the shortest path from S to node 6, I can tell you the distance is 25. Yeah, I can immediately tell you the length of this path. What is a bit more difficult is to tell you what is the actual shortest path. For this I have to go into this edge 2 array. And what I have to do is, if you ask me for what's the shortest path from 0 to 6, I have to start at 6, and I have to look at this edge here. So the last edge on the shortest path goes from 2 to 6. It's that one over here. Okay, so that is the last edge. So then I have to go to node 2. That's 5 to 2. So this is the edge over here. So I go to 5. 5 is 4 to 5. That's the edge over here. And then for 4, it's 0 to 4. It's this edge over here. So if you are interested in the actual shortest path, you go from the end to the beginning. And you follow this. These edge 2 values or these parent pointers. So this is then the shortest path is the one over here. It's 0, 4, 5, 2, 6. And all of these edge 2 values give you such a shortest path tree. Yeah, so this is these shortest paths, they actually give you a tree structure that you can then easily navigate. This is Dijkstra's algorithm, like the basic idea. Are there questions? Okay, so the important thing here really is, like, there are rounds. In each round, you pick a node, you relax the edges, and then in the next round, you look for what is the non-tree vertex, that's how they put it here, that has the current lowest, this true value. And you do this blindly, one after the other.
So with the marathon, I have to take all, with this algorithm, you have to take all possibilities?
Like all the
vertices in a map.
Okay, yeah, it's good point. Yeah, this algorithm says single source shortest path. If I tell you like I want to go from somewhere in Copenhagen to somewhere in Copenhagen, you start this algorithm, it's still going to tell you this is the shortest path tree for Denmark. And please now just follow these parent pointers, these h2 values, and that's how you find the shortest path. So this is a bit stupid, of course. And we'll talk about what you actually want to do when you have a different question, and that is the question that you have in your routing project, some user types from and to, and you actually have an ending node, you have a destination. Yeah, and basically you stop once you would consider this destination. That's what we do. We'll see this in the live coding session. You're not?
No.
Okay, so okay, so the question is, now I'm only considering shortest paths from, I'm interested in what is the shortest path from a node S to a node T. Of course, I can read that off from the result of this here, but this might be 20 million nodes or something on the map of Denmark. So what you would do, if you are only interested in the length of a shortest path to node T, is you do Dijkstra until you consider node T. Yeah, at some point, Dijkstra's algorithm says, and now consider this destination node. And once this is done, you say stop. Because then you know the shortest path to T, and you would only add more nodes from there. And the correctness is, like, I hope Tore kind of said to you what the idea of this algorithm is. Like, the idea of the algorithm is, once you consider a node, once you say, now I pick this node, then you can be sure that the value that is in here is correct. Yeah? So you update these values all the time. But the idea is that once you say, and this is the one with the next smallest, this true value. At this point in time, you can be sure that this is the correct value. It's never going to be updated again. Okay. Okay, then let's switch back. This was Dijkstra's algorithm on this very high-level view. Let's talk about where does this graph come from. I mean, I showed you a graph, but you're not interested at all in this like 8 vertices graph. You're interested in what is the graph behind my current OSM file. Yeah, and I would advise you to, at the beginning, to make it as simple as possible. So you know, like a street in OSM is represented by a way. And this way has many different attributes. And the most important for building the graph is what are the nodes that are on this way. Okay, and let's say there are 2 ways here, and there are 6 different nodes here, and the OSM data would look like this. So there's way, and it says on my way I have 1, 3, 4, and that's this path over here. And the other one says on my way I have 2, 3, 5, and 6. That's the one over here. And all you do is you say, well, all my nodes are the nodes that I find in my OSM file. All my ways is just, I put edges here between 2 and 3, 3 and 5, 5 and 6. Like that, in the most naive way possible. Yeah? That's how you build your graph. It's going to be very, very large. Like dependent, of course, on your on the file that you're currently considering, but this is how you get the graph. The straightforward solution is really to have an edge between each of these segments. Of course, actually, it's quite, for example, having this edge over here, you might consider removing such cases. Yeah, here, so you have 3, 5, and 6, and usually in this OSM data you have like one street is represented by many, many, many different nodes. Yeah, and you could think about only splitting ways at intersections. That means merging these 2 edges into one. That would help your Dijkstra quite a lot in performance. Yeah, because there are fewer edges and nodes in the graph. But I would suggest do it as naively as possible. Look at this OSM data and just say, I know all of these nodes, and now I build all of these edges in this straightforward fashion. Okay, then if you look at your project, the project description, there is this bullet point 12 of the actual requirements, and that one says, well, you should allow the user to choose between routes for biking and walking and for cars, and then the car routes should take into account speed limits, they should take into account expected average speeds. And if I give you a route for biking and walking, that one should always be the shortest, like an actual distance, and please don't use highways. Yeah, it's which is, I think, a pretty obvious requirement for for these route suggestions that you give the user of your program. Okay, you'll see that this graph is actually pretty large for the whole map of Denmark. So so no option is to build these graphs for all of these different cases separately. Yeah, please don't do this. There should only be one graph. And what you should rather do is, I mean, here's the suggestion that you have a class edge, and such an edge has different parameters. It knows its length, it knows its speed limit. You can read off the speed limit. I guess you have seen that by now. You can read off this speed limit usually from these way tags, or somewhere in the way there is a tag that kind of tells you about that. Is it one way? All of these things should be stored with an edge. And then if you call Dijkstra, please route from source to destination, then you should also say by car, and I'm interested in fastest route. Yeah, and that should tell your Dijkstra implementation, okay, now so now I have to consider fastest routes, and for example, a fastest route, what you would do is, what you would consider is that so this is this edge UV, and what you would do is you have a distance, maybe as your standard weight for this edge. But if you're interested in actually travel speed, like how long does it take, then you should divide by speed limit. Yeah. And that is how you then, is this correct? Yes. And please make sure that it's like at the right unit. I think I did some live coding yesterday and was wondering about, this doesn't make sense at all. Like, what is this fastest route? How does it look like? Because I think my distance here was in like centimeters for some reason. My speed limit was in kilometers per hour. Like the output made no sense at all. So please make sure like if your units are correct here. Okay, but this is like, so whenever you consider an edge, you might only be interested in distance. You might be interested in distance over speed limit to get in, this is how long I expect someone to take, how long I expect it to travel among this edge. Okay, and then you can say highway, and that is that, for example, if a user says, now I'm interested only in bikes, then you relax, and your Dijkstra algorithm classically says, now relax all the edges. But of course, like if you're on your bike and you see an edge that belongs to a highway, then you just say, okay, I skip this. And that's all you need to do here. Yeah? So your Dijkstra takes parameters, and then you only consider certain edges, and you always adjust the weight to your current situation. Questions? Okay, so some more tips. That is what was asked. So in your routing application, you're only interested in the shortest path between a pair of vertices, not all the vertices, and you stop Dijkstra as soon as the target node is added. And then this manipulation of weight, that's what I just say, check whether an edge is admissible for current vehicle type before relaxing it. That's what I just said. Okay. Let's see how this is going to work out. And I'm going to do something, I hope you don't hate me, but it's, I wanted to do it in Java, but then I actually have like when I did my PhD, my very first project was like improving route planning algorithms. So I have some background and some other frameworks somewhere around. And I don't know if you're going to see what's going to happen, but we're going to do like the live coding session this time in JavaScript. And I've heard that you learned JavaScript in one lecture in like this other class. I don't know. It's such a complicated Danish name that I always forget it immediately. Okay, what we are going to do, is this the correct one? This is the correct one. And please don't say at the end, oh, why don't we do this? Like, why do we care about all of this Java stuff? Yeah, why don't we build like a something that uses HTML, something that uses JavaScript? There are many different reasons for you doing your project. And there are some things that I just can't do, which are going to be super easy for you to do. Yeah, because you're in a much, your implementation is going to be much faster. Okay, so what I'm going to do here is I have this basic framework that I usually show students like when they come to the university and want to find out like, oh, how do algorithms work and stuff like this. So I usually talk about route planning algorithms with them. And I already have this backbone. And it's all in JavaScript, so we have to kind of implement Dijkstra in JavaScript here as well. So what I can do here, I can say start and destination, and it says some street name and city name down here. Then I can choose the method, and that's going to be a bit more interesting at the very end of this lecture. And I can say compute route, and it doesn't say anything because there's no implementation yet of Dijkstra's algorithm to actually work with this data. So let's start with the implementation, and I hope you can see that. Yeah. First of all, how does my graph look like? So I took like Copenhagen.osm for this for this example here, and my graph is I have basically a class for nodes. And a node has longitude, latitude, and it has a rank. Please not consider the rank. It's going to make sense of the very end of the lecture. And all a node has is this list of adjacent vertices. That's my graph structure. You see there are no annotations here. Yeah, that's something that you have to add. So for me, the whole graph is a list of nodes. Each node is longitude, latitude, and an edge. Okay, this is going to take a while. An edge. Okay, the edges come down here. And this is all static. Yeah, so there is one thing that moves, that transforms an OSM file into this graph data structure here. And then I just say, for this very first node, you have an edge to this node, this node, this node, this node. And that was it. Yeah, and this is actually travel time. So this is the edge weight. And please disregard this very last entry here. This is the whole graph. Yeah, so I don't have a class for edges here. I just say a node is an object, and it has a list of adjacent nodes. That's the data structure. Okay, very simple, very straightforward. Let's do Dijkstra. Dijkstra gets this list of nodes. It gets a source node, it gets the destination node, so that's the one, those are the ones that we see over here. And we initialize our elements, and this is also something that I do differently, which is a bit worse for performance, but I think it's much easier to read. Like, I don't have a dis2 array, but for each node I store its dis2 value as an attribute to the node. Yeah, which makes it so much easier to actually know what's going on. This h2 value for me, it's always a parent. So this is like this h2 value that you have, but I rather call it parent. The parent node and the shortest path tree. That's what I want. And then to get a nice visualization, this discover order tells you how did Dijkstra explore this graph? So which nodes were added at which point in time? Okay, we start from this, and all we know is that the source has this true value of 0. Yeah, that's our initialization. That was everything, and I already set all the others to infinity. So this is the initialization of the algorithm. All the parents are null. And now, what I want to do is, I want to start an infinite loop. That's always, what do I want to do? I always want to start a while loop. Okay, Well, what is Dijkstra now asking us to do? It asks us, what is the next node I should consider? So this while true loop, that's a round. Like each run through this while loop is a round. So now I'm interested in what is the next node that I should consider. And I'll implement it as stupid as possible. It's not going to work on the whole map of Denmark, but it's still going to work. Yeah, and it will show you some limitations and something where you clearly see, okay, that this has to be improved. So I say, like, the next node, current. What do I have to go? Please remember this picture. There was this long array. I have to go through the long array and find the minimum value. That's what I'm going to do. Okay, and this is another function, get minimum. Okay, and we do it straightforward. We say the node, we don't know which node to return, and we don't know what the minimum is going to be. So this is infinity, and we go through all of our nodes, and I hope that I think the syntax is, even if you don't know JavaScript, I hope you can read what's going on here. Okay, so I go through all of these nodes, and I always ask, is the dist2 value of this, is the dist2 value of node I smaller than what I've seen so far? And if it is, then I should update this one, and then node I is my current guess on this is the minimum node. So I just go through this array. Okay. Now if we actually look at our example, there's something that is missing here. Like usually a start of the round looked like this. Yeah, so we had this array, but some of these elements were grayed out, and I always said like, oh, we don't consider them. Yeah, and if we compare this to our current implementation, this is not at all what is done here. It always goes through all of these nodes. So we kind of need some additional attribute that tells us, oh, this node has already been added. So let's add such an attribute as well. And let's call it, is it added to tree? And let's say in the beginning, they are not added to the tree. And only later on, like at this point in time, I say, now I picked a node, so I added it to this tree. Okay, so this is just a status marker for each node. Have I considered you already or not? And then I can ask, then I can require from this node that it shouldn't be added to the tree here. Okay, so this skips all the nodes that were grayed out, basically. Yeah, and this should be a correct implementation of where we get this minimum. Okay, and then the algorithm was, I look at this current node, I relax all the edges, that's it. So let's go through all of these nodes, neighboring nodes. And now I have to check how we're, okay. And these neighboring nodes were in this adjacency list. Okay. So the neighbor here is current.adjacent_i. That's neighbor I of our current node. We relax neighbor I, so we ask, is the distance that I know to the neighbor larger than if we would use the path over our current? And let's talk about distance. I have this weight function here which gives you the distance, I think in centimeters, between two nodes. Weight current neighbor. Okay, so this is, let's look at this. So this is current distance to the edge weight. Is it better? Does it improve the current value that we know for our neighbor? If it does, then we set neighbor.dist2 to current.dist2 plus our weight. And we say, if you want to go, the parent of neighbor node is the current node. And we show this path tree because we updated this value. And what do you say?
Yeah, you should change the for keyword to if.
Oh, yeah, that's a great formula. Thank you. Yeah, so if if it improves our distance, then we update the value. And this should be pretty much, hopefully, the thing that we did, like very boringly, round after round in the example. Now we have the beauty of JavaScript, so if it fails, I have no idea why it fails. Let's see, we go from Istelgale to Erstels Boulevard. Yeah, I mean, it's very slow, so. Okay, so now you see JavaScript debugging at work. We go to the console, it says, cannot set property added to tree of null. So there's something is null. Added to tree. Must be up here. Where's the typo? Cannot set property added to tree. Oh, okay. Yeah, I mean, like, I started very confidently with this infinite loop. And if you look very closely to this infinite loop, it's really never stopping. So I should better check, like, I mean, so if there is no more node here, then it will return null. Okay. So there we go. So if it's, and let's just reload this and let's leave this debugging thing open here. Aha! So there is this shortest, but this is not, but I forgot something. This is not the moment where you should say ooh, because the moment where you said ooh, where I should woo about these things is, I forgot to add this cover order here. So this is, we look at this current node. Pay attention. Okay, we go the other way around, and this should work, hopefully. So this is, so this is what Dijkstra's algorithm is doing here. Yeah, and this is the very stupid thing it does. Yeah, it goes through the whole graph that it knows and then says, aha, there it is. This is the shortest path. Okay, and you see, like, so there are 19,364 different nodes here that it settled, and the obvious way of improving this is asking when current is our destination node, then we break. Okay, and then it's both. I mean, it's much faster. And it stops as soon as this destination node is the current node. Okay, but this is how Dijkstra's algorithm works. This is also like the visualization, because you go by these two values, you basically always get this circle-like shape. Yeah, it looks a bit off here because of all this water in Copenhagen, but you always get this circle-like shape. Questions on this basic part here? Yeah, and you see the implementation is, I mean, it's super stupid. Every round, it goes through all of these nodes and asks what's the new minimum. And then you update like 2 of these values and you say, okay, let's go through these 20,000 elements again to ask what is the current new value. Yeah, and you can improve that. Okay, if there are no questions, let's take a 10-minute break until 11 and then continue. Second part. We are going to talk a little bit about some implementation details and then on how to improve this. This is going to be, I mean, it seems to be pretty fast already, but there are many nice ways of improving Dijkstra's algorithm if we talk about route planning. Okay, so first, so what did we do here? We had a very slow implementation of this minimum function. Yeah, always going through all these nodes and checking what is the new smallest node. That's something that you shouldn't do. But let's talk a little bit about certain differences. No. There we go. n vertices, m edges. Question is, how do we find this next node, where we then want to relax all these edges? Our solution is the solution 1. I mean, we go through this long array of these 2 values and we say, that's the next one. The running time this is going to have is like in each step, we go through all of these nodes, that's O of n in each step, and then we have to do this n times because each single node could be extracted once or is considered once, but at most once. So this is n times n, this is O of n squared. This is going to be, this is good enough for Copenhagen, but it's going to be a bit slow for Denmark. Okay, so what you actually want to do, and you should know that already, is what you can do is you have a node and you have this 2 value, and you're always interested in what is the node with the minimum value. This is exactly what a priority queue is going to tell you. Yeah, this is what they are made for. You have a bunch of elements, and you're always interested in what's the element with minimum priority now. Yeah, so you put all of these elements, here nodes, into a priority queue, and their priority is this 2 value. Okay, and now there are 2 solutions here, and one is very easy to implement, and the other one is a bit more tricky and is considered in the book here. So the idea is we keep all of these nodes with these 2 values in a priority queue. If we do this eagerly, and eagerly means that each node is in the priority queue at most once, then the running time is O of m log n. And usually for road networks you have seen, or you can also imagine that, like usually you don't have a lot of edges, like with each connected to each vertex. I gave you this picture, like usually you have straight lines, and sometimes you have an intersection. I think for Denmark the average degree of a node is 2.3. Yeah, so 2 is something on a line, and then there are, like an intersection is usually 4, it's 2.3 is the average degree. So you have very few edges. So this is something like n log n. In general, the running time is m log n. I don't know if you still remember why this is the case. Basically, for each edge, you do this relaxation. You look at the endpoint and ask, is this 2 value now improved? Is it smaller? And if that is the case, and you want to store each node at most once in the priority queue, you need a priority queue that allows you to decrease the priority. Yeah, this is usually called a decrease key. And this has logarithmic running time, and you have to do it, or you might have to do it for every single edge. So this is this running time statement here. It's m log n. Okay. But the problem is that you need this decrease key operation. You have to say, those are the elements in my priority queue. This element over there, its priority was updated from 15 to 12. And there are some priority queues implementations that can do this. Java's priority queue doesn't do this. So there's no way of decreasing a key. And I don't know if Tore already told you a little bit why this is it's difficult to support decreased key operations because you have to know where the element is. So the priority queue has to keep track of, if somebody tells me decrease the priority of this element over there, this element is currently sitting in this heap at this position. Yeah, there's a lot of bookkeeping, and most of the algorithms don't need this decreased key operation. Yeah, so they decided to just skip all this bookkeeping and don't allow to do decreased keys. So what can you do when you don't have decreased key operations? You do this lazy variant. Yeah. So whenever you see an edge, you relax, you don't know, and this 2 value improves, then you don't say decrease key, but you rather say I insert the very same node again. Okay, so you just blindly insert whenever this 2 value is updated. This can have the effect that a single node is in the priority queue many times. Yeah, but that's, and like they make a big deal, quite a big deal out of this issue. Yeah, in general, like you shouldn't care about this. You can care about this if you want a challenge. Then use a priority queue, do it yourself with the decreased key operation. But in general, if you just blindly insert, then for each edge you might get an insertion. And there might be, for every edge, there might be an element in this priority queue. And then you look at the running time, so you have m operations, and you have m elements in your priority queue, so this is m log m and not m log n. But asymptotically, it's the very same number, because a graph, like the number of edges, is at most the square of the number of vertices in a complete graph. Yeah, and then you take the logarithm of this n squared, and you see, oh, this is just 2 log n, and it's the very same running time asymptotically. Of course, you would notice a difference, yeah, but it's not a big deal. Like, you can just use Java's priority queue and insert elements blindly, and it's going to be fast enough, and much, much, much faster than what I just showed you, going through this dist2 array all the time. Okay, so that's the message I'd like to convey. Don't make this big deal out of something that you don't see asymptotically. Yeah, it might take you an additional day to implement this priority queue. Yeah, please first do it. Do this lazy variant here. What you never should do is try to be very smart and clever and try to do something with Java's priority queue that you might think it makes complete sense, but running time-wise, it's like the worst thing you could do. Like Tales from the Exam, this actually happened. So one group, like their final product, that was the relaxation, which is a very fine relaxation. But then at some point, it asked, like, it did decrease key by asking priority queue, do you know this element? And if you know it, you first remove it, and then you insert it again. Yeah, and this, I mean, like if I have no idea about running times, I think, oh, this is smart. Yeah, it doesn't have decreased key, so I just ask, do you know this element? Yeah, and if you do, I remove it. A lot of comments. Like, I mean, maybe that's also clearly a sign that something fishy is going on if you think like, this all is clear, but then you have this 4-line comment for the single line about what's going on here. The problem is that asking a priority queue, do you know this element, is like the worst thing you can do. Because then it goes through this heap, like checks every element, and returns true or false. Yeah, cool. Like, and this is slow, so for every operation you get a O of n. Like for every single edge, you get n time. So this is n times m. I think it's much, much worse than just going through this distance array like I did it. Yeah, please don't do it like this. Yeah, either blindly insert or take on the challenge of using this decrease key operation and implementing that, but don't do this. Okay, that's all I want to say implementation-wise. Yeah, you can go from what we did, and then you just put a priority queue on top to not go to search for the minimum in this priority queue, and you're good to go. That should be Dijkstra, perfectly fine Dijkstra implementation. And performance-wise, it shouldn't bother you that much. Okay, let's still talk about improving Dijkstra, and this is more a conceptual point of view, like what can we do? And so what we saw is this, this is like how this shortest path tree looked like for one special query. And it's always a bit difficult to see that in Copenhagen, but what you basically do is like you grow a circle. Yeah, and once the circle kind of hits your destination, you're done. Yeah, but there's no goal orientation whatsoever. Yeah, it's like you go south into like Indreby, but you're on the other way, you are here in Bellahøj. Yeah, so there is no goal orientation here. It's just a circle. What I want to show you is this A star heuristic. And for the very same query, like what is the difference here? Dijkstra looks at 1945 different vertices, and A star looks at roughly half of them only. And this is by adding a goal orientation. A star is also some like kind of a buzzword. Like I think some of you in your bachelor or master thesis, they will use A star because it's just a very common heuristic to improve shortest paths. How does this A star heuristic work like? Let's look at so this Dijkstra algorithm, you proceed in order of distances, to your starting node. Yeah, and A star is Dijkstra's algorithm, but with a different priority. And that gives you a different order in which your vertices are considered. And you could think about, like, if you were to know, like, all of these shortest paths, you should take a minute at home and think about what would happen if the priority of a node is the distance of the from the source to your to a node plus the distance of the node to the shortest path to the destination. Like, this is the priority in Dijkstra's algorithm. What if this would be the priority? You would just say get minimum all the time and run Dijkstra's algorithm. And I say this is ideal. And it's really, I mean, it will go directly to the destination, not look at anything else, and still be correct. But the problem is, of course, you don't know these distances. I mean, you currently run Dijkstra to get these distances, so you don't know that. But you should think about, like, why is this this is basically optimal. Okay, but we don't know it, and A star is you add something to the distance to your current node, not the distance to the target, but rather some heuristic value. Okay, and that is the A star algorithm. It's going to be like 2 lines in our current code base to go from Dijkstra to A star. And the question is, like, how do you choose this priority over here? Like, what is this heuristic? And then you go to these old papers, and let's say the heuristic that is only so a node has a certain value to it, and all you demand from this value is that the value is at most the actual distance to your target. Yeah, if this is the case, so if the heuristic always underestimates this actual distance to your target, then this is a heuristic that you can use to find shortest paths. And if you want to use, like, Dijkstra's implementation, like do the exact same thing that Dijkstra does, then you need something that is a bit stronger, and that is called consistency. So if you see an edge, u to v, it must hold that these heuristic values here, that h of u is at most this weight plus h of u. So this has to hold, this condition has to hold for every single edge. Then it's called consistent. And there's a reason why you need this consistency. The question is, what could such a heuristic be? Because the heuristic is super simple for you. Yeah? The heuristic is just, you want to go from a node to your target. You don't know how long is the actual path. But what you do know is, like, if you were to fly from here to there, what is the distance? Like, what is the straight line distance geographically? And this always underestimates the actual distance. Because, well, this is the kind of optimal way to go there. But usually you have to maybe go like this. Okay, but the heuristic is, it underestimates the actual distance because it's the best way to get from a starting node to a destination. If you think about travel time, you have to do something else, and the heuristic actually gets much worse by doing this. So if you are interested in in travel time, then each of these edges, they look like this, distance over speed limit. And then underestimating the time to go from a node to another node is still like, what is the distance? But you divide by what is the maximum possible travel speed. Yeah, so like in Copenhagen, I guess it's even true for Copenhagen. What you would do is, like, you have 3 kilometers, and you know by car you can't go faster than 120 kilometers per hour. And that's your heuristic. Like, if it would be a highway straight from your point to the destination, that is the heuristic value that you choose. Okay, and let's just try this out. So let's do A star, and A star is choosing nodes with a different priority. Yeah, so like Dijkstra's algorithm, this down here stays the same, but the way we pick nodes is a bit different. And the way we pick nodes is that we add to our dist values the distance if we were to fly from node I to our destination. Okay, and to make this fast, we pre-compute this. So like this nodes I estimate to dest. So what is, to go from node I to the destination, I can just ask here in my program, what is the straight line distance? I think it's in centimeters from node I to our destination. So this is a single value for each node in the graph, and then I just add this over here. So whenever I consider a node, I also add this estimate. Estimated distance. Okay, this is the A-star algorithm. Yeah, the only thing you have to really make sure is that this value here really underestimates the actual distance. Yeah. Okay, let's see. I mean, this is now okay. This is going to be a bit tricky because I have to reload. So I have to kind of find these points again. This is basically ITU, isn't it? And this is like there's a triangle here. Let's see if I find this point. We think about Dijkstra's algorithm with 3,470 nodes. That's how much he had to consider. Okay, let's try to find these points again. It was over here, and we were interested in the path to over here. And now it should be this heuristic, and it shouldn't be a circle, but it should be a bit more goal-oriented. And it should work. Let's see. Okay, and this is the A-star heuristic. Yeah, so you see that basically that it really, I mean, it's difficult to see. Let's take another one here. Yeah, that it really tries to move into this direction. Yeah, and it's correct if the heuristic underestimates the actual distance. Let's look at something where it's a bit non-obvious. Let's go, say we want to go from Islandsbrücke to Fisketor over here. I have no idea what's going to happen. I mean, it's really focusing on going through this Stuhlhaunen channel over there. Yeah, but it's still, I mean, it's still pretty nice. And the, I don't know if you saw this, like I think it was 500 something. Were the number of nodes that were traversed by this A-star heuristic. So that's an improvement of a factor of 6, factor of 7 in your running time, because you have to look at far fewer elements. This works best for shortest paths if you're interested in distance, because the heuristic becomes much worse if you talk about travel time, because then you always assume, okay, the heuristic says what would be if there is a highway from here to there. Yeah, this is always the heuristic value it compares to, so it doesn't help that much. We can also check this. I mean, I have fastest. How do I have it? Get fastest. No. What was it called? Get traversal time. Get traversal time. And then down here, I don't use these weights. But traversal time, I mean that's, sorry. Traversal time is the actual edge cost here. No, and I can also use, but this might be very slow, let's see. Neighbor. So let's see if I talk about traversal time, how these things look. And it's usually a bit worse. Let's see. From there to there. Yeah. What could have? I think I did some. This here, I mean, this should be okay. This is the edge weight. Up here, estimated. That's also traversal time. I'm a bit. Yeah. I mean, I have traversal time also. Oh no, okay. Traversal time is the fastest possible time. It's a bad name for a method. Like traversal time is really if everything would be on a highway. I'm interested in edge cost of I. Edge cost of I. Yeah, sorry. I mean, why should this help? I don't know. Let's see. Okay. Any ideas? I mean, I didn't change a lot here. Maybe. I mean, it's pretty confident. Went through. Just. Yeah. Any ideas?
You said the edge cost of I instead of current.
Yeah, but this like current to neighbor, this part?
Yeah, you said edge cost there before.
Yeah, but it's I mean this is like the straight line. Like this is the straight line distance in like centimeters. I mean, is it?
What does get traversal time do?
It gets the. Oh, yeah. That's very unfortunate. Yeah, this is not supported. I'm very sorry. Yeah, there's another method here that yeah. If I were to implement Dijkstra on the actual graph, yeah, this will, yeah, okay. The problem is that this is going to be infinity for these nodes here. Let's see. I want to go from, yeah, and I think like traversal time would be, it might be in meters. So let's see, 36 meters per second. I mean, that's pretty fast, isn't it? Carry probability of undefined. Okay. Why did I start doing this? What did I want you to show? I mean, that was the... Yeah, I don't know why this fastest route somehow doesn't work for now. But I mean, the message is that it becomes much worse because the heuristic is much worse because it always says like there is a motorway, like there's a highway between these two nodes. Yeah, and it's not going to be as nice as the A-star algorithm in this traditional form. Okay, but I hope the idea is clear. I think I don't want to spend time. Now I told you that there is this correctness idea, and yesterday evening nobody tells you really why this is correct. Like what's the point in this condition? Yeah, and so I thought about it, but it's going to take a bit too long to actually describe this, why this is correct. But the basic idea, once you have this, once this consistency is true, what you know is that once, so this is what Dijkstra's algorithm usually does. Then you take new priorities, never mind. But the problem could be that now you say, now I take this node, and there's a shorter path to this node. Yeah, let's say it goes over here. Yeah, and then I do some calculations down below, if you're really interested in it, to show you this path here, it cannot be shorter than the current one found. Yeah, it's not that much, but I think I don't have time to spend. Unfortunately, I don't have time to do this here. Yeah, it's not that important, but it's consistency. Only if you have this consistency condition over here, you can say that whenever I pick a new node, I'm sure that this is the new shortest path, to the actual shortest path, that I know the shortest path. Okay, but don't have to mind about these things. Yeah, it's like, you can use A star if you want. I hope you have seen it's very simple to use A star. It comes almost for free. Yeah, because you just modify these priorities. Okay. Questions about this A star? Yeah, sorry that it kind of didn't work out with this fastest running time. Yeah. I'd say there's no reason to not use it if you already have like functions that give you this is the distance between 2 points, this is the travel speed between 2 points. What I would like to talk about is in the very end, like very briefly, still give you like an idea of what's going on, efficient route planning. Dijkstra is already pretty efficient, then you take A star and it's more efficient, and then some companies like Google and others came up with the idea, oh, wouldn't it be great if you have like a web application and then people can choose to go from, or can look for shortest paths? Like, I mean, that's pretty new, such applications. You couldn't think about a system supporting this in like 2000. And still all these little devices that you have made, that you maybe have in your car, that shows you this is how you go from A to B, all of them is A star. Yeah, for a single user, all of them implement A star. It's basically very simple. If you're a web server and you want to answer like 1,000 of these queries per second, then you really don't want to use A star. Yeah, you want to do something faster, and this is then efficient route planning. And I just want to show you why I didn't continue pursuing this research area, because they basically solved that, and it's in use by Google. And let's talk about what they do. So efficient route planning, the idea is that you use some shortcuts. We'll talk about that. But like, let's see, from over here to over here, they add 72 vertices to the shortest path tree. So we started, I mean, we went from here to there, and we had something like 3,000 and then 500. They do it from there to there in 72. Even cooler is they do it from Aalborg to Copenhagen in 300 or something. Yeah, this is pretty cool. How do they do this? So, like, first of all, it might not be a problem for you because your query times will be pretty okay already. Yeah, single user static setting, fair enough. Only if you want to have fancy stuff like dragging the endpoint around. Then you might think, doing a Dijkstra computation all the time, that might be too slow. Then it might be better to have a fast implementation. There's a footnote here that I don't talk about right now, but let's talk about a technique called contraction hierarchies. It's a paper from 2008, and yeah, it's really beautiful. What they do is they start with the graph, and each node gets a rank. Yeah, you just number them through. Let's say completely arbitrarily. One node becomes rank 1, and the other one, and then you number through until n. And then you say, okay, let's all sort them according to their rank. And then preprocessing is, for each node, you say, oh, please contract this node. That's why it's called contraction hierarchies. The basic operation in preprocessing is contraction. And I have an example on the next slide, but let's just go through this contraction on the blackboard. So let's say we have a node V over here that we want to contract. And there are nodes U1 and U2 over here, and there are some nodes, let's call them W1, W2, and W3 over here. Let's add some edges between those. Let's add some edges here and there. Let's say all of these edges here are 1. What do I want? I think I want them to be, let's say this is 3. Let's say this is 2. Let's say this is 1. This is 3, and this is 4. This is the input graph. Ranks don't matter. This node is the next one that is going to be contracted. Contracting means you basically assume the node wouldn't be there. And then the question for route planning is, if I remove this node and I were just to remove all of these edges, would I lose important shortest paths in my graph by doing that? And just let's look at this example over here. So we think about this node as not being here. Okay, and then the algorithm says for each pair of incoming edge and outcoming edge, check, is this path over node V a unique shortest path? So let's check this for these two nodes. We can go from U1 to W1, and it takes us 3. Is there another path of length 3 in here? Yes, there is one over here. So that is not a problem. Yeah? Even if this one is removed, none of the shortest paths, there is still another shortest path of the same length. So this is not important for shortest paths. The same thing here, length 4, but there's length 4 here, length 5, but there's length 5 over here. So basically, this one is fine. What about that one? We remove node B, and we see now from U2 there are actually no outgoing edges. Yeah, so we might have, I think we have removed some shortest paths, but which did we remove? There was a shortest path of length 3 over here. If V is gone, there's no shortest path of length 3. There is actually no path. So what we do is we add an edge here. This is this. Add a shortcut UV with weight, sum of these edge weights. We do this, then we ask, what about U2 and W2? And we see that you always take the shortcuts that have been added into account. So from U2, implementation-wise a little bit different. But let's say, let's do per graph. The shortest path is of length 4. But now there is another path of length 4. Yeah. So this is fair. We don't need to add this edge. We could do it, it doesn't hurt, or no, it doesn't make it incorrect, but this is already length 4. Same here, length 5, but there is length 5 over here as well. The result of this contraction step looks like this over here. Okay? One shortcut added, all of the other edges removed. Okay, and that's what you do during preprocessing. So you contract each of these nodes, you remove them, you might add some shortcuts. And now you should ask yourself, now we add a lot of these edges. Yeah, we make the graph only larger. How does it help? How does the query algorithm look like? And it's really not obvious why this is going to work. But what you do is, you look at your source node and you look at your target node. So source and target, so over here. And now you have this large graph. And in this large graph, you have the original graph, and you have all the added shortcuts. It's much bigger than the original graph to begin with. What you do now is you make a Dijkstra, full Dijkstra run from S. But there must now be one trick, because now the graph is much larger, and I say now do Dijkstra. Find all shortest paths from this node. And the trick is that you only consider edges that go up in rank. Yeah, this rank was the node ordering from the beginning. So you only consider an edge if it points to a node that was considered later in the graph. From T, you do the same thing, but you do it backwards. So you do all the edges. You flip all the edges, and you do the same thing. So you say, I only look at them if they go upwards, in the original graph if they go downwards. That's the computation. You'll find some nodes here, you'll find some nodes here. What do? You look at all the nodes that have been found by both of these algorithms, and you just ask, like, what's the distance from S to this node plus the distance from this node to T for all of these, and you take the minimum. And you say, that's the shortest path. That's contraction hierarchies. So it's like a bidirectional Dijkstra on a very special graph, yeah, where you have these ranks and they seem to not have a union. And it's like 1 hour of proof to show you why this makes sense. Yeah? So these paths that are considered in this way, you have And if you have a rank over here, you know that these paths that are found in this way, they go up in rank to some peak, and then they go down in rank. What you basically want to prove is that for all of these, whenever you have a shortest path in this overlay graph, you find the shortest path that has this form and is of the same length. And it's really not obvious how to do this. But if you then run it, and let's just see. Now let's switch to, this should be Denmark. Should have loaded that before. Is there something else? Yeah. It's really not obvious how this works. But it's actually pretty easy to implement. That's nice. So here we are in Denmark. Just to show you, like these contractions. So what I told you about the preprocessing. So what the preprocessing algorithm is going to do, it's going to take all of these. It takes all of these nodes, it orders it, and then does the same thing for every single node. It kind of looks like this. Yeah, and it's really, you don't have to do anything. It's kind of automatically. And it's also interesting, like, for this algorithm, like, what is the most important point in whole Denmark? It's, I was pretty surprised. I thought it must be on Sealand, but it's somewhere in, close to Odense. It's this highway intersection here. Like, this is the most important point in whole Denmark for this algorithm. And if you then ask for, okay, let's say we want to go from Aalborg to Copenhagen somewhere, and now we say we want to use contraction hierarchies. Then it looks like this. Yeah, it looks at 300 nodes and says, there, oh, that's the result. Cheating, quite a lot of cheating. It only uses this overlay graph. I mean, you can see like what it, you can see a little bit what it did. Like I think it only, like this intersection here. There was only a single vertex, and the single vertex was actually this very important like intersection close to Odense. Yeah, where these two highways like seem to cross each other. Yeah, and this is the forward search. This was the backward search over here. This was the node in the middle. And then the problem is like finding out what was this actual route. Yeah, this route is much longer than 300 nodes. Yeah, and this route was why there were like each node here has contracted nodes. Yeah, so these contracted nodes here, like whenever you see a node here, you know there is another node 10,600. No, that's the rank of the node. So this number here, this is when it was considered in this contraction process. And if we go down here, these edges tell you, was this an original edge or was this added during the contraction? And whenever you see something like this, then you know, there was the node of rank 7,339. That was the node in the middle here. And then you can go back to the original graph. And I mean, it's like, it's super cool. I mean, it's, I don't know, when I saw this, I couldn't believe that this works. Yeah, and then you go through this proof and you see, it kind of makes sense. Like you can actually, like there are always these steps that go like this. And you can prove this by induction. And but it's completely not obvious why this works. Yeah, and you have to do something. And you have to do a full Dijkstra. When I saw the paper, I thought, okay, now they do full Dijkstra computations. This must be slower. But then, if you only go up in rank or down in rank, there are very few nodes that you actually consider. Yes?
Could you just touch on the rank property again? How you chose them arbitrarily?
Yeah, it's like,
do anything for us.
Yeah, it's like you don't choose them. Like every single ordering is going to work, but some are worse than others. Like, if you want to, what's the best, like, if you choose if you do it arbitrarily, you're going to add a lot of shortcuts that are not necessary. Yeah, it's like, in the paper they will tell you a lot about different, so what they, for example, the thing that is actually implemented here is you do it arbitrarily. No, you don't do it arbitrarily. You sort by each vertex here gets as a priority queue, the number of incoming edges times the number of outgoing edges. That's how many shortcuts you might have to consider. And then you sort all of them by this number. And this is like from lowest to highest. And then whenever you do a contraction, you might add some new shortcuts and you rearrange those elements because they have more incoming edges. Yeah, and you rearrange them all the time. So you want to keep the number of shortcuts to be added. You want to consider nodes such that you know that that you make sure that not too many shortcuts are added at a too early point in time. Yeah, you also see this here, that this is not arbitrary, but it's spread out. Yeah, it's okay. I mean, sometimes it does a lot of things in Sealand, and then all of a sudden Jutland comes up. And but this is like spreading out the cost of these shortcuts computations. And you have to do something better than arbitrary ordering. But what I want to say here is, so this is the first note actually, that this ordering makes a big difference, and there are many possible solutions. In the paper, they tell you about some of them, which they implemented and what worked well. I think I just took this incoming edges times outgoing edges, and that worked well. Yeah, and this is this rearranging dynamically. Once you have new shortcuts, others might to switch and move their rank. You never want to remove vertices or edges like I tried to do here. You just say, I don't consider them. And yeah, and right. And what I also told you is like, oh, it's very simple. Like there's this layer short, there's length 3. There's this length 3 path over here. Is this one unique? And what you basically have to do is you have to run a Dijkstra all the time. Yeah, you have to find out, like, if I remove this edge, like, do I still find this node in 3 steps? And this is going to be far too inefficient if you run Dijkstra all the time. Yeah, so you have to apply some heuristics. It's also in the paper. And it's like running Dijkstra for 30 different vertices. Okay, but the good news is, if you add some shortcuts unnecessarily because your algorithm said, I'm not sure if this is unique, it doesn't matter. It makes running time a bit slower, but it still works. Okay. Last, how to get from the distance of the shortest path to an actual shortest path. This is what I showed you. You have to store the contracted nodes with each edge, and then you have to, yeah, how do you call this? So you have to go to each edge and or you have to go to each node and say, this was the shortcut, and I used it. Then the actual path was going from here to there, and there, like this, yeah, iteratively. Yeah, but the performance is very nice. Like Google, when they give you a short, I mean, first they have a large cache. Yeah, that probably what you looked into was something somebody else was interested too. So they get a cache hit, and it's very fast. Then first they give you the distance, because this can be done much faster. But it's basically this system. Yeah, what they use, and you get query times like in the microseconds if you implement it really correctly. You will get query times like 1 to 2 milliseconds, something like this, if you do it like this. Okay, and it's just much, much faster. This was a pretty bad query, but that was Dijkstra 8000. A star actually looked at 4,700. These shortcuts, I think it was like 300 something. And you've seen, this shortcut algorithm, these contraction hierarchies, it doesn't matter if you go from Aalborg to Copenhagen or somewhere within Copenhagen. Like, difference is very small. Like for Dijkstra, it's tremendous. Yeah, and it's like a really algorithm beauty. Like, that's why I started doing algorithms. Yeah, because it's completely non-obvious that this works. Yeah, and it improves something that people try to improve for a long time, and the implementation is actually not that difficult, and you get really good running times. So if you want a challenge, try to include that. I would say it takes you 1 week.